Marginal field. A field is labeled as a marginal field when there are 1. Very small sizes of reserves, pooled to the extent of not being economically viable. 2. Lack of infrastructure in the vicinity and profitable consumers. 3. Prohibitive development costs, fiscal levies and technological constraints. A marginal field may be converted into commercial field if there are changes in technical or economic conditions. It is thus crucial to select a suitable structure for marginal field. Based on our study, we selected buoyant leg structure or BLS, which provides highly advantageous system for deepwater oil field development and usually used with a shuttle tanker. Meanwhile, in hydrodynamic and structural analyses and model basin tests, BLS is proved well suited for utilization in ultra-deep water, and the overall cost of the structure is favorable when compared to TLPs and spars. The common characteristics of BLS are as below. 1. A mobile offshore drilling unit, MODU, is used to install the combination drilling foundation template. 2. MODU is used to drill the wells and support the upending and installation of both BLS large and small diameter cylindrical shell components. 3. Large diameter leg associated with controlled ballasting while free flooding for small diameter leg which will upend the structure. 4. Top entry connection will be used as to secure the small diameter leg to the foundation leg. 5. A 4-legged deck structure will be barged which either set on top of or lift installed onto the large diameter leg. Another common characteristics of BLS. The ballasting process will continue until ballast equal to deck weight is pumped out. The BLS unit is stable in free-floating mode and to partially pretensioning and restraining the leg. To obtain final system pretension, further deballasting will be performed. Remote subsea connectors will be used to run and secure conductor to the wellheads. Circular frames with built-in guides will provide the conductors with lateral support at regular intervals. This slide shows different configurations of BLS that can be applied are shown in diagrams. Figure 2 exhibits wellhead facility of BLS unit, while Figure 3 exhibits marginal field production facility of BLS unit, followed by a table to differentiate between these two configurations, which can be divided into deck structure, buoyant leg, restraining leg specifications and the forces involved in each configurations. Based on this table of data, marginal field production facility of BLS unit have a high buoyancy rate compared to wellhead facility of BLS unit. Neutrally buoyant and stable structures in a free-floating mode. Natural heave period, 22 to 30 seconds. For 1,000 meters water depth site, depending on the axial stiffness of the small diameter restraining leg, natural heave period, 2.5 to 3.5 seconds. In Figure 4 shows buoyant leg cross-section, while Figure 5 shows restraining unit cross-section. Structure components and applied loads. Reduced applied loads and the symmetrical configuration of the proposed BLS as well as the pretensioned leg all contribute to minimize roll, pitch and surge effects. Compatible BLS and conductor motion and subsequently lower conductor curvature and stresses. Providing lateral supports for conductors. Providing storage for produced crude oil. Large diameter leg provides sufficient buoyancy to support the deck structure, and to pretension the BLS. The BLS is tethered to the seabed by a single small diameter tubular flooded during upending. The structure is stable in a free-floating manner, and deballasting of specific partitions ensures enough pretension for the tethering of the BLS to the seabed. System pretension of the leg and conductors constrain heave motion. Structure components and applied loads. Operational requirements. Presumed that a MFPF unit can be utilized as extended production test facility, EPTF, or early production, EPF, to produce from 2 or 3 wells, with regular offloading of the processed and stored crude to a shuttle tanker. The decision to make the unit as MFPF unit is normally taken in the case the field is confirmed to develop and, in the case, more wells are to be added. In table number 2, shows the site characteristics such as water depth, nearest facility and nearest refinery. Environmental data such as extreme event and operating conditions involved are also shown in this table. Other environmental circumstances considered in conceptual development, extreme loop current condition and resonance waves conditions. Due to the compliancy of the structure, the applied wind wave and current forces on the MFPF BLS unit are considerably reduced. Acceptable pretension serves to counter the lateral loads triggering offset. Material are made from high-strength steel plates for the large and small diameter tubular shells and stiffeners respectively. The BLS was modeled on computer for time history analysis for operating and extreme environmental conditions as follow. A 120 seconds steady-state plots showed fluid kinematics, BLS displacements, velocities and accelerations, as well as the loads. Applied loads and BLS tension forces were all consistent. The peak hydrodynamic load on BLS, from 6 megantons, for the WF unit, to around 20 megantons, for the MFPF unit. In 1995 Koppel and Kapanoglu found that the rotation of the buoyant leg under extreme environmental condition varied between -2.2 and +7.1 degrees with maximum deck level acceleration, about 18% g. Close to the deck level accelerations calculated for a small size TLP at the Gulf of Mexico. For investment economics, setup of the drilling template, foundations, and the initial reconciliation of 10 wells, estimated $103.5 million. Total price of producing, transporting, and installing the floating, and keeping legs of the MFPF, estimated $62 million. Structure, transportation, and installation of the deck shape, and equipment, estimated $36 million. Addition of $8.5 greenbacks million on the value of producing, transportation, and installation of the template and foundations. The full investment amount is $210 million. The OPEX for a 10-year lifestyle of the sector, envisioned at $184 million. The manufacturing profile, starting from a peak of 48,000 barrels in step with day and swiftly declining to 10,000 barrels according to day, is used to acquire a recoverable reserve of 50 million barrels consistent with day. Using Deepwater site in Gulf of Mexico as example, following assumptions were made. Royalty equals 12.5%. Cost recovery limit equals 100%. Depreciation rate equals 5 years SDR. Line. Profit 01 once built contractor share, percent, BOPT equals 100%. That is, simple royalty, tax system. Income tax, effective, equals 34%. Contractor effective after tax built equals 58%. And by spreading the capex over a year construction and setup period, an inner rate of return of 42% is obtained. The usage of net gift price approach yields $201 million. Here are some comparison been made. For BLS unit compared to full completion floater unit. BLS is a standalone device. Meanwhile floater completion floater, SCF, requires a tanker, FPSO, to handle and store crude oil. Comparing BLS unit to SPA unit. BLS has minor movements while moving, while SPA is susceptible to noticeable movements during rough weather. The cost comparison between all three structures are as follows. BLS, $106.5 million. SCF, around $80 million. SPA, installed at 600 meters of water in the Gulf of Mexico, around $11 million, excluding the drilling program. Thank you.